Tonight, we're going to imagine something that physics says is impossible, and then we're going to use it anyway. Imagine that we cracked it. Imagine that every barrier fell away, every engineering limit, every problem with fuel and mass and energy, and we built a ship that could travel at the speed of light. The fastest thing the universe allows. Nothing in all of existence moves quicker than this. It is the hard ceiling written into the laws of reality, the one number that nothing, anywhere, has ever beaten. Even at that speed, even moving as fast as the universe will permit anything to move, it still won't be enough. Not even close. By the end of tonight, you're going to understand exactly why the cosmos is built on a scale so vast that the ultimate speed limit feels almost like standing still. And why some places in the universe are not just far away, but permanently, eternally out of reach, no matter what we invent. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with the speed itself, because to feel the disappointment that's coming, you first have to feel the thrill. Light moves at 186,282 miles per second. In a single tick of a clock, a beam of light crosses a distance greater than 7 times around the entire planet. In terms of speed per hour, light travels about 670 million miles every hour. These are numbers that don't fit into anything you've ever experienced. A bullet leaves a high-powered rifle at around 2,000 miles per hour. A jet fighter, at full afterburner, might reach about 1,500 miles per hour. The fastest spacecraft humanity has ever built, the Parker Solar Probe, screams through space at around 430,000 miles per hour when it whips past the sun. That probe is the fastest object human hands have ever made. And light is still more than 1,500 times faster than that. So when you imagine a ship that moves at light speed, you are imagining the absolute pinnacle of what motion can be. There is no faster. This is the top. And it should feel like cheating. It should feel like the universe has been conquered. For a little while, it almost is. Before we go anywhere, it's worth pausing on how we even know the speed of light, because the story is one of the quiet triumphs of human cleverness. For most of history, people assumed light was instantaneous. You light a candle, and the room is lit at once. There seemed to be no delay, no travel time, nothing to measure. The great thinkers argued about it for centuries without resolution. Some insisted light moved infinitely fast. Others suspected it had a speed, but had no way to test the idea. The breakthrough came in 1676 from a Danish astronomer named Ole Rømer. He wasn't even trying to measure the speed of light. He was studying the moons of Jupiter, specifically the innermost large moon, Io, which dips behind the giant planet and reappears on a precise schedule. Rømer noticed something strange. When the Earth was on the side of its orbit closest to Jupiter, the eclipses of Io happened slightly earlier than expected. When the Earth was on the far side of its orbit, the eclipses happened slightly later. He realized what this meant. The light carrying the image of Io's reappearance had farther to travel when the Earth was farther away. The delay wasn't a change in the moon's orbit. It was the time it took light to cross the extra distance. From this, Rømer made the first real estimate of the speed of light. His number wasn't perfect, but it was the right order of magnitude, and far more importantly, it proved something profound. Light has a speed. It is fast, but it is finite. It takes time to get from one place to another. That single insight changed everything. because it meant that looking out into space was the same as looking back in time. Over the following centuries, the measurements grew sharper. In the 1800s, scientists like Hippolyte Fizeau and Léon Foucault devised clever experiments using spinning-toothed wheels and rotating mirrors to clock light over distances here on Earth. They sent beams across miles of open air and timed them with mechanical precision that seems almost unbelievable for the era. Later, Albert Michelson refined the technique to extraordinary accuracy, bouncing light between mountaintops and measuring the tiny time it took to return. Each generation pushed the number closer to what we know today. And what we know today is exact, because the speed of light is now built into the very definition of distance. The meter is defined by how far light travels in a precise fraction of a second. The speed of light isn't just something we measure anymore. It's the ruler against which all distance is set. That's how fundamental this one number is. It is woven into the foundation of physics itself. There's a deeper question lurking here, and it's worth sitting with for a moment. Why does light have a speed limit at all? And why that particular speed? When we say the speed of light, we're really talking about something far more fundamental than light. We're talking about the speed of cause and effect itself. Light just happens to travel at that speed, because light has no mass, and anything with no mass travels at the maximum the universe permits. But the limit isn't really about light. It's about how fast any influence, any signal, any piece of information can pass from one place to another. If you flick a switch here, the effect of that action, the ripple of cause spreading outward, cannot reach a distant place faster than this speed. It is the rate at which the universe updates itself. It is the speed of this caused that. That's why nothing can beat it. If something could travel faster than light, it could, in a sense, arrive before it left, and cause could come after effect. The orderly flow of events that makes reality make sense would unravel. So the speed limit isn't an inconvenience the universe imposes on us out of spite. It's the very thing that keeps cause before effect, that keeps the story of the universe in a sensible order. Light is simply the messenger that travels at this ultimate pace, carrying the news of every event outward across space, never faster, never slower. And light is a strange messenger. It has no mass, no weight, nothing you could hold. It is pure energy, woven from electric and magnetic fields that take turns creating each other as they ripple through empty space. Visible light is only a thin slice of a far broader spectrum. The same kind of waves, traveling at the same speed, include radio waves and microwaves at one end, and ultraviolet, X-rays, and gamma rays at the other. All of them move at exactly this one speed. When we look out into the universe, we're catching these waves as they arrive, decoding the messages they carry from across unfathomable distances. But every message takes time to arrive. And that simple fact, that light is fast but finite, is what's about to make our journey so humbling. Now picture yourself on board this ship, looking down at Earth, ready to leave. You fire the engines, and instantly you are moving at the speed of light. The moon is the first thing you'll pass. It sits about 239,000 miles from Earth, on average. At your speed, you reach it in just over 1.25 seconds. You blink, and the moon is behind you. The same trip that took the Apollo astronauts 3 full days, you've just done in less time than it takes to clear your throat. Already, this feels miraculous. Next comes the sun. Our star sits about 93 million miles away. That sounds enormous, and by human standards it is. But at light speed, you cross that entire gulf in about 8 minutes and 20 seconds. Think about what that means. The sunlight, warming your face on a summer afternoon, left the sun's surface more than 8 minutes ago. If the sun were to suddenly vanish, you wouldn't know for 8 minutes. The Earth would keep orbiting an empty space, bathed in light from a star that was already gone. That is the reach of light speed inside our own neighborhood. It makes the inner solar system feel almost small. Let's keep going outward. Mars, when it's on the far side of its orbit from us, sits around 250 million miles away. You'd reach it in around 22 minutes. Jupiter, the giant, lurks roughly 484 million miles from the Sun. Light from the Sun takes about 43 minutes to get there. Saturn, with its glorious rings, is around 890 million miles out, about 1 hour and 20 minutes at light speed. By the time you reach Neptune, the outermost true planet, you're nearly 2.8 billion miles from the Sun. Light takes about 4 hours and 10 minutes to travel that far. So, in a single afternoon, moving at the ultimate speed, you could cross the entire planetary system, from the Sun all the way past Neptune. Even on that afternoon, though, something would surprise you. Empty. That's what the journey would feel like. For all the wonder of the planets, the spaces between them are overwhelmingly empty. You'd leave the Sun, and for many minutes there would be nothing but black, until tiny Mercury slid by, then the bright crescent of Venus, then the blue marble of Earth and its small moon. Beyond Mars, you'd cross the asteroid belt, and despite how it's often pictured, you would almost certainly see nothing at all. The asteroids are real, hundreds of thousands of them, some quite large, but they're spread so thinly across such an enormous volume that the average distance between them is hundreds of thousands of miles. Spacecraft have flown through the belt many times, and the danger of striking anything is so small it's almost not worth considering. You could fly straight through and never glimpse a single rock. Then would come the long stretches between the giant planets, vast gulfs of darkness with Jupiter, Saturn, Uranus, and Neptune appearing as rare islands of color in an ocean of black. This is the first lesson the universe teaches about itself. Space is mostly space. It is named perfectly. Even our own solar system, the most crowded and familiar piece of the cosmos we know, is almost entirely emptiness, with a few small worlds scattered across it like lonely lighthouses. And if the solar system, held tight by the sun's gravity, is this empty, then the gulfs between the stars and between the galaxies are emptier still, by amounts that defy the imagination. The afternoon journey across the planets isn't really a tour of crowded sights. It's a passage through a great deal of nothing, punctuated by a handful of precious worlds. That emptiness is the canvas on which everything tonight is painted. It's why even the fastest speed imaginable spends almost all its time crossing the dark, with the destinations few and far between. This is where the illusion is at its strongest. This is the moment where it seems like light speed has tamed the cosmos. You've crossed the solar system in an afternoon. Surely, the stars can't be that much harder. Hold on to that feeling, because it's about to break. Beyond Neptune, the solar system doesn't simply end. There's a vast region of icy bodies called the Kuiper Belt, home to Pluto and countless other frozen worlds. This is a broad, flattened ring of ice and rock left over from the birth of the solar system, never quite gathered into a planet, drifting in the deep cold far beyond the last of the giants. Out here, the sun is no longer a warm disk in the sky. It's a brilliant point of light, blazing brighter than anything else around it, but giving almost no heat at all. And noon would look little different from a moonlit night back on Earth. Pluto is just one resident of this frozen ring, joined by other small worlds with names like Eris and Makemake and Haumea, each one a sphere of ice and rock circling the sun across centuries. Beyond that, the sun's influence stretches on through a thin scattering of comets, and then, far out, a great shell of frozen objects called the Oort cloud. This cloud is thought to begin thousands of times farther from the sun than the Earth is, and to stretch out to perhaps 1.5 light-years away. It isn't a flat ring like the Kuiper belt. It's imagined as a vast spherical shell wrapped entirely around the solar system, a faint cocoon of perhaps trillions of icy bodies, each one drifting alone in the dark, so far apart that a comet out there might have millions of miles of empty space in every direction before its nearest neighbor. Every now and then, a gentle nudge from a passing star or the slow tug of the galaxy sends one of these frozen wanderers falling inward. And centuries later, it arrives in our skies as a comet, trailing its long, bright tail, a visitor from the very edge of the sun's domain. And here, for the first time, that word appears. Light years. Not light minutes, not light hours. Light years. The Oort cloud, still technically part of the sun's domain, still loosely bound to our star by gravity, is so far out that crossing it at light speed would take you well over a year. The little ship that crossed from the sun to Neptune in an afternoon would need more than a year just to leave the sun's frozen outer suburbs behind. And that's still home. That's still our own front yard. We haven't even started the real journey yet. This is the first hint that something is deeply wrong with our sense of scale. Inside the planets, light speed felt unstoppable. But the moment we step past the planets, into the true space between the stars, the same speed begins to falter. The distances stop being measured in minutes and hours. They start being measured in years. And they will never go back. This is the right moment to make sure we understand what a light year really is, because everything from here on out depends on it. A light year is not a measure of time, even though the word year is hiding inside it. It is a measure of distance. It is simply how far light travels in 1 year, moving at that staggering speed of 186,000 miles every second, never slowing, never stopping, for an entire year without pause. That distance comes out to nearly 6 trillion miles. 6 trillion miles in just 1 light year. We switch to this unit for a simple reason. Once you leave the solar system, measuring in miles becomes useless. The numbers grow so enormous, so crowded with zeros, that they stop meaning anything to the human mind. Saying, a star is 25 trillion miles away, tells you almost nothing. It's just a smear of digits. But saying it's a little over 4 light years away tells you something you can hold. It tells you that light, the fastest thing there is, needs 4 years to make the trip. The light year quietly carries the speed limit of the universe inside it. Every time you hear that a star is a certain number of light years away, you're really being told the minimum number of years it would take to get there, at the absolute fastest speed reality allows. So when we say the nearest star is more than 4 light years away, that's not just a distance. It's a warning. It's the universe telling you, in its own units, exactly how long even the fastest possible journey would take. And the deeper we go tonight, the larger those numbers grow, until the light year itself, 6 trillion miles at a stretch, starts to feel small. To understand why the stars are so impossibly far, you have to understand the emptiness between them. Inside the solar system, things are relatively close together, held in tight by the sun's gravity. The planets feel spread out, but compared to what comes next, they're practically huddled together for warmth. Between the stars, there is almost nothing. The space between us and the nearest star is not filled with anything you could land on or even see. It is emptiness on a scale that the human mind simply was not built to hold. Let me give you one image to carry through the rest of tonight. If you shrank the sun down to the size of a grain of sand and placed it on a table, the nearest star, also shrunk to a grain of sand, would not be across the table. It would not be across the room. It would sit around 4 miles away. 2 specks of sand, 4 miles apart, with absolutely nothing in between. That is the true emptiness of the galaxy. The stars are not crowded together like lights in a city. They are scattered like a few grains of dust thrown across an entire ocean. And our ship, moving at the fastest speed the universe permits, must cross every single inch of that emptiness, 1 second at a time. This is the part that breaks the illusion. Speed only helps when there is a reasonable amount of distance to cover. When the distance is this immense, even infinite speed would barely help, and we don't have infinite speed. We have the speed of light. And the speed of light, it turns out, is heartbreakingly slow against a backdrop this large. Now we come to the first true wall. The nearest star system to our Sun is called Alpha Centauri. It's actually 3 stars bound together by gravity. 2 of them, Alpha Centauri A and B, are sun-like stars orbiting each other. The third is a small, faint red dwarf called Proxima Centauri, and right now it sits slightly closer to us than the other 2. Proxima Centauri is 4.24 light-years away. Let that sink in. At the speed of light, the fastest anything can ever travel, it would take 4 years and 3 months to reach the nearest star. 4 years of nothing. 4 years crossing pure, empty darkness, with the sun shrinking behind you into just another point of light, and the destination star growing so slowly you'd barely notice the change from 1 month to the next. And here's a detail that makes it more poignant. We now know that Proxima Centauri has at least 1 planet orbiting in the zone where liquid water could exist. It's called Proxima b, a world, possibly rocky, possibly with some kind of surface, circling the nearest star to our own. The closest, potentially habitable world we know of, our best first destination if we ever leave the solar system. And even that, the very nearest one, is more than 4 years away at light speed. Proxima Centauri is the close one. It's our next-door neighbor. If you wanted to visit Sirius, the brightest star in our night sky, you'd travel for about 8